All right, so I want to work some example problems of how we use Newton's second law, F equals ma. But before we do that, we need to take some time to readdress this idea of vectors and how we work with vectors in mathematics. Because F equals ma is a vector equation. It says that the force F is equal to the mass of an object times the acceleration of that object. And again, the way we use this is we figure out what the forces are and then use the forces to tell us how the object's going to move. Not the other way. We don't use you can use the mass times the acceleration of an object to measure the force acting on it, but that's not where the force comes from. The force doesn't come from an acceleration or a deceleration. The force causes an acceleration or a deceleration. Okay, so again, in order to do this, we need to readdress this idea of vectors because we're going to need to do some mathematics. And it's kind of hard to think about doing some of the important mathematics that we need to do on the quantity F equals ma without really thinking about these vectors and how to address them. So let's suppose that we have this vector A and we have this vector B, and we have some angle theta between them. Well, we've learned some operations. Some of the operations that we've learned are how to add them. So we have an operation called addition, and that's the head to tail. And then we learned how to multiply them by numbers. So I'm going to put a dot here, though we don't usually use a dot to indicate this, but this would be this is scalar multiplication. And then we also have another kind of dot, which I'm going to draw as a bigger dot, that we learned is called the dot product. And there was a big difference between these two kinds of multiplication. The head to tail method is something that starts with two vectors and gives you a new vector. The scalar multiplication is something that starts with one vector and gives you a new vector. And the dot product was something that started with two vectors and gave you a scalar. It gave you a simple number as the answer. And we'll see examples of these in each of the as we move forward in looking at things like work as an example. We'll see where we need to use these kinds of things. But so far, we've only defined how to do these geometrically. In other words, we've done them on arrows. These arrows, we figured head to tail meant something like this. You know, we take this one, we add them together, and we get a new one. And we could say this is vector A, and this is vector B, and this is vector A plus B, which we might call a new name. We might call it vector C. So we could say this is vector A plus B equals C. And as you can see, this is but we worked out how this works, and it makes sense as addition for vectors, but you're not. It would be hard to imagine doing other kinds of mathematical operations on these arrows, these abstract vectors. So it would be nice if we could figure out some way to turn vectors into numbers, and this is something that we naturally do all the time. So let me give you an example. Suppose we were looking at a displacement vector. So here's our origin. Say this is where we started, and this is the place that we ended. And say this is on a map. So we're looking at a map, and of course we have north pointed this way, and we have east pointed this way. And what we might say if we were trying to explain to someone this path of travel that we went from here to here, you might say, well, the first thing you do is you go 5 miles east, and then you go say 3 miles north, 2.5, 3 miles, whatever this length here is, and that will get you from here to here. So notice what we've done is we've broken down this thing into some components that run in the directions of our coordinate system. You say you go this direction in our coordinate system a certain distance, and then you go this direction in our coordinate system a certain distance, and that gets you the same thing as going from here to here. So what we've actually done is we've changed this arrow from being just an arrow or a vector that we might call A. We might say, well, that A represents moving 5 miles east and then moving 3 miles north. And so we might represent that vector by saying it's the numbers 5 and 3. So and you have to know what this means. You need to know that the first number is how far you go east, and the second number is how far you go north. And then any vector that you draw a vector like this, and you might say that one is minus 1 mile and then plus 1 mile. So that would be minus 1 mile east would be 1 mile west. So you would go west 1 mile, and then 1 mile north would be up. And so you can recreate any set of directions, any vector on a map with naming these sort of coordinates, or what we call in mathematics, we call them components of a vector. So let's make that rigorous. What we're going to do is find out how to rethink about each one of these operations, but think about them in terms of numbers, which we're going to call components of a vector. So how are we going to do that? Let's take a vector. I'm just going to make an arbitrary vector, some big vector A here. Okay, and what we're going to do is, to do this, to put components in, the first thing you have to do is you have to put in a coordinate system. So I'm going to put in a coordinate system like this. And instead of calling it north and south and east and west, I'm going to call this axis y and this axis x. That's what we typically use in mathematics, as opposed to north, south, east, and west. Okay, and furthermore, we're going to define this direction as positive and define this direction as negative, and this direction is positive y and this direction is negative y. And then these lines just correspond to the real line. So this is the real line, a copy of the real line going this direction, and a copy of the real line going in this direction. And now the next thing that we're going to do is we're going to establish a unit. So we're going to make some arrows that represent 1 unit. So I'm going to make an arrow. Actually, let's do it this way. Let's do it in a different color, just to make it very clear. I'm going to make a unit vector going this direction, and I'm going to call that unit vector y with a little hat over top of it. And I'm going to make a unit vector going in this direction, and I'm going to call that x with a hat on top of it. So what do I mean by unit vectors? What I mean by unit vectors are vectors that point in the direction of our axes, but are only 1 unit long. So whatever unit we choose to use. On a map, you might use kilometers, or you might use miles. Typically, when you're mapping out something smaller in the SI system, you would use meters. But there's some unit here associated with this, and this is one of those lengths. Okay, now, what did we do with the map? You said, well, we went 5 miles east. Well, that would be saying that 1 unit is 5 miles, and you went 5 of those units to the east, and then you went 3 of those units north. So what I would claim is that if we take these unit vectors, we can use scalars to multiply them, and then we can add them and get any other potential vector that we could ever draw on the plane. Any other arrow that I could draw anywhere, I can make as a combination of these 2 vectors. So the first thing I would do is, if I want to write down the vector A, the first thing I would do is I would take the unit vector in the x direction, and I would multiply it by some scalar. We're going to call that a sub x, and we're going to multiply that by the unit vector in the x direction. So we take this and we multiply it by a number so that it's this long, whatever the unit happens to be. So now this new dotted vector, this dotted line vector, is ax times the vector x hat. By the way, these little hats on top of x and y just stand for unit vectors. Instead of using arrows, we put the little hats on when we're saying they're 1 unit long. Whatever unit we're using, they're 1 unit long. Okay, and then what I'm going to do is I'm going to do the same thing for the y vector. Okay, I'm scaling it up to the same height as this vector over here. So you'll notice that this piece matches here, and this piece matches here. And so now what I have is additionally an a sub y times the unit vector y hat. And then if you'll notice, if I take this blue vector and this red vector and add them together, what do I get? If I take the blue vector and the red vector and add them together, we'll do this in, let's see, some other color. We'll do this in orange. It's not very pretty, but it'll work. So what do you do to do a vector addition? You take the head to the tail. So here is the first vector, and then I want to take this blue vector and move it over here. Maybe I should just do it in blue. Move the blue vector over here, and here's the same vector, the blue vector. I've just moved it I've just transposed it from one side to the other. And so that's still the vector ay y hat. And now I go this way this far, and I go this way this far up, and that gives me this. So what I can say is that the vector A is the sum of some scalar times x plus some other scalar ay times y. And so these two unit vectors get multiplied by these scalars and added together to give me the vector A. And it doesn't matter what vector I choose. Let's choose another vector. Let's do it in black. Let's choose another vector. We can always find what's called the x component. That would be the x component of this vector. Let's call this vector b. And so we would have b sub x. That would be the x component of the vector this way. And then the y component would be this way. And that would be b sub y, and that would be the y component. Notice in both cases, both b sub y and b sub x here are negative numbers. So we have a negative number for the x component and a negative number for the y component. Here, both of them are positive. We had a number a sub x is positive, a sub y is also positive. So I can write down any vector that I want to as some combination bx x hat plus by y hat as some combination of these two vectors. So then my next question might be, is there a way to add these two vectors? And is that way equivalent to adding any two vectors? So let's just do this. So what we're going to do is we're going to add a plus b. So what is a plus b? Okay. Well, that's going to be equal to, I have an ax plus bx. So that's just going to be ax x hat plus bx x hat. But here I can factor out the vector, it's the unit vector. So I can factor out this x hat and then just add ax plus bx. So let's rewrite that. Let's rewrite that as quantity ax plus bx times x hat plus, do the same thing over here, I'm going to get ay plus by times y hat. So what does this tell us? First of all, is this the right picture? Let's clear some space here so that we can see if this makes sense. In other words, is this the exact same thing as what we did geometrically? Is what we did geometrically exactly the same thing as what we're doing algebraically here? This is called the algebra of vectors. So let's see if they are in fact the same thing. So what would we have if we went? Let's draw a coordinate system here, and let's say that we had, this was our first vector a, and this was our second vector b. Okay, so this is a, and then this is b, and we're adding them together to get a new vector c. So we're adding them, so this is the vector a plus b. Is that the same thing as this? Well, let's look at the x component first. So the x component, this piece here would be a sub x. And then this piece here would be b sub x. But notice from here to here, this piece here is ax plus bx. And that's the component of this bigger vector. So this part's right. This is the same thing. And you'll see you get the same thing here. If we go up this far, that's a sub y. And then if we go up this far, that's b sub y. And if you add these two together, that's this vector, this addition vector. That was very ugly. I'm sorry about that. That's the vector c. That's the component c sub y. So what we get is that if we take vector a and b and add them together, all we have to do is add their components. So the x components add together and the y components add together. It gets really big pain to write this over and over again this way, so we introduce a new notation. We say that the vector a is equal to the components ax, bx. This hides a lot of information. It's saying that there is a standard x unit vector that we've chosen, a standard, excuse me, I just completely botched that. Let's try this again. Not b sub x, a sub y is what I meant to put there. My apologies. A sub y. So this says that there is a two standard unit vectors, one in the x direction and one in the y direction. And then we take this number ax and multiply it by the x unit vector, and we take this number ay and multiply it by the y unit vector, and then we add those resulting vectors together, and that gives us this vector a. So this is a representation of the vector a. And again, it's exactly like, and this is exactly like what we saw before. This basically says you go this far on the x-axis, and this says, and you go this far on the y-axis, and then you draw your arrow from here to there. And that's the vector a. Okay, and we also likewise have the vector b is going to be b sub x and b sub y. And then the vector c, which is equal to a plus b, so the sum of those two vectors, what is it going to be? Its components, it's a plus b, so its components are just the components of a and b added together. Ax plus bx and a y plus by. Okay, and so this piece here we would now call cx, and this piece here we would now call cy. So we have a way of, instead of drawing vectors and adding them by drawing them, we now have a way of doing them algebraically, just using these numbers to add the vectors. In fact, I'm not going to go through the rules. We have a rule for each one of these. So if, let me clear some space off here. If we have a geometric rule for adding and multiplying and dot product, we also have a rule involving the components. So these are the geometric versions, and they're completely equivalent. They're all completely equivalent. One is just looking at them from the geometry, drawing the pictures, and one is looking at them algebraically, using algebra on the actual components, the numbers themselves. So the algebra of these vectors, we still have a plus, but for this we just we add components. So the vector a plus b is going to be equal to the component x of a plus the component x of b. That will be our x component for the sum vector, and then ay plus by will be the y component of our vector. So that one we just proved. Then we're going to have the scalar multiplication, which again I'm just going to show as a simple dot. But that would be, we take some scalar number, I'll call it lambda. We typically use a Greek number for scalars. Lambda times some vector a. And what that's going to be is, if you know the components of a, then you just multiply each component by the same lambda. Okay? And then we also have a dot product, the blob product, but the dot product. And the dot product is, remember, that's taking two vectors, a dotted with b. And here I didn't write down what the dot product was. It was the magnitude of a times the magnitude of b times the cosine of, plus the cosine of, plus magnitude of a plus magnitude of b times the cosine of theta, the angle between them. Sorry. In this one, it's very easy. The dot product, you just multiply the components. So you would take ax times bx, and that would give you, and then you add that to ay times by. And in fact, I don't need a vector symbol here because the product here is a scalar. The product is a scalar, not a vector. So let's just get rid of that. So you get to choose, basically. You get to choose between the geometric representation of your vector and the component representation of your vector, and you get to use whichever one you want. Why is this important for f equals ma? Because f equals ma, we can write the vector f as having components. It has an x component and a y component. And the scalar multiplication rule we know that A also is a vector, so it has some components A sub x and A sub y. And by the scalar multiplication rule, then we can write down that this is also going to be equal to, because f is m times a, then we can also write this down as m times ax plus m times a, not plus, excuse me, sorry, comma, m times a sub y. In other words, we can write down some non-vector equations. F sub x is equal to m ax, and we can write down f sub y is equal to m a sub y. In other words, we can separate the acceleration and the force into components, into x components and into y components, and we can just solve the equations just using the components without ever having to draw the pictures. And as long as we know how to convert back and forth between the geometric and the algebraic versions of these things, then we're good to go. So the last little piece here is, how do you do that? How do you convert between the geometry, which has to do with lengths and angles, and the algebra, which has to do with components? So how do we convert back and forth between those two? So the last little thing we'll do in this video is go through that process. So let's say that I give you a vector and tell you its components. Let's say that here's a vector A, and I give you its components, and its components are 5 and 2. All right, so let's draw that vector, and let's figure out what its length and angle is from looking at this vector. So we're going to go over 1, 2, 3, 4, 5. So 5 says go 5 in the x direction, and then we're going to go up 2, 1, 2. So this is my point, and then I draw an arrow from here to here, and that's the vector A. Okay, now what we would like to do is figure out what is the magnitude of A, what is the length of A. A equals what? Remember, this is the magnitude or length of the vector. And we would also like to know, what is this angle? We would like to know what is the angle here, to that the direction that we would need to go. So if this were on a map, this would be the bearing. So can we go between, you move 5 miles east and 2 miles north, to you move a certain number of miles in a straight line at a bearing of, I don't know, whatever that happens to be, 70 degrees, whatever it happens to be. We're going to find out what it is actually in just a minute here. Can you do that? Can you translate between the components here and this angle and this length? Is that possible? All right, let's start with the length first, because that's the easiest one. So what we're going to do is build a right triangle here, and we have this length, which is a sub x, which we know is equal to 5. And we have this length, which is a sub y, which we know is equal to 2. And what we're going to do then is just use the Pythagorean theorem. Remember, the Pythagorean theorem says that the length a squared is just going to be a x squared plus a y squared. Or that the length a is just going to be the square root of ax squared plus ay squared. So that's our rule. This is our rule here. We can erase this question mark now. We know how to get the length of the vector. The length of the vector is going to be the square root of the x component squared plus the y component squared. Okay, so let's do that for this one. So we're going to get ax is 5, so that would be 5 squared. And then ay is 2, so that's 4 squared. So let's see, what is that? That's going to be 25 plus 16, so 35, 41. So a squared is equal to 41. So in this case, the length of this vector a is going to be the square root of 41. I'm not going to bother putting that into a calculator. But now I know exactly how long it is, and I can get it from the sum of squares of the sides and taking the square root of the sum of squares. So that's just Pythagorean theorem. That's easy enough. I'm going to redraw this again, zooming in a little bit so it's a little bit easier to see. So once again, I have this triangle where the vector itself is my hypotenuse, and I have this angle theta. Okay, so there's my angle theta. That's the angle that I'm trying to determine. And if you'll remember some trigonometry, we know that the tangent of theta is going to be equal to the opposite over the adjacent. So that would be AY divided by AX. Or we can just simply say that theta is the inverse tangent or the arc tangent of the y component divided by the x component. Okay, so that's our rule for getting theta. So this is very, very simple. Let me, let's write that down again. So arc tangent or tan inverse, whichever one you prefer, it's the same thing, of the y component divided by the x component. So let's figure out what this angle is in our particular case for our vector 5, 2. So for our vector 5, 2, we would have that the angle theta here is just going to be the inverse tangent of 2 divided by 5. So I will go ahead and punch that into a calculator. If I pull a calculator out here so that we can do that very quickly. And I get 22 degrees. So this is approximately 22 degrees. All right, so this is how we go from, if we have components, we can use the components to figure out how long our vector is. In this case, our vector was square root of 41. That was its length. And we can figure out what its angle is relative to the x-axis, and here it is 22. I will point out that you do have to be a little bit careful about this. Pay attention to which axis your angle is being measured from. So if you've got a vector pointed off this way, when it's measured against the x-axis, you're going to get a different number in the way the tangent works. So just be careful that you know which angle you're talking about when you use arc tangent to get that angle and what it's relative to. So if you were looking at a vector over here, you would actually have the angle from the negative x-axis. If you want it from the positive x-axis, you would have to take your answer and subtract it from 180 to get this larger angle from over here. But nevertheless, these are the ways that we go back and forth between, the way we go from the components to our lengths and our angles. What if we are given lengths and angles? Let's say that we have a vector A, and that vector A is 10 units long. The length of A is 10 units, whatever it happens to be. And let's say that the angle it makes is 52 degrees. Okay, so we've got this kind of picture here. We've got something coming out this way. We know the length here is 10, and we know the angle here is 52 degrees. And now we want to know what is the y component, and we want to know what is the x component. And again, we're going to use trigonometric functions. So what do we know? We know that we have the sine of our theta. So this would be the angle theta. The sine of theta is opposite over y over 10. Or let's call it a sub y. That's the terminology we've been using, a sub y and a sub x. So this length divided by 10 is this. So what we can write is that a sub y is equal to 10, which is the length of A, times the sine of theta. And similarly, we can write down that a sub x is going to be the length A times the cosine of theta. So this one is the adjacent over the hypotenuse would be a sub x over 10 is equal to cosine of 52 and then multiply through by 10. So this is how we go if we want to go from length and angle to components. If I tell you that I went 10 miles northeast at 52 degrees from the east axis, then, and I wanted you to tell you how far you had to go east and then how far you had to go north to match me, how would I come up with those components? It's very, very easy to do that. Let's do it in this particular case. So I'm going to do 10 times sine of theta. So 10 times the sine of 52 is equal to 7.88. So this length here would be 7.88. And then this length would be 10 times the cosine of theta. And I get 6.16. So what this is saying is if you go 6.16 miles east and then 7.88 miles north, you'll end up exactly the same place as if you went 10 miles at 52 degrees north of east. Okay, so this is a way of going back and forth between the components, which we will use to do algebraic manipulations, and the length and angles, which we will use when we're thinking about drawing the actual arrows.